Hello everyone and welcome back. Last time we studied chain maps, which were maps on a chain complex which commuted with the boundary operator. This time we're going to learn the analog of homotopies for chain complexes. And as a consequence of this, we're going to learn that the homology of a space is invariant under chain homotopy equivalence. So let's get to it. Let me just remind you of what we did last time. So last time we had a map on topological spaces, f from x to y, and we learned that this induced a map on the level of chain complexes, which we called f sharp. And this was very easy. Remember, an element of a chain complex, like the singular homology chain complex, is a map from a simplex into the space. And if I just compose that map with f, I get a map from a simplex to y. We also learned that this had a special property, which was being a chain map, which meant that if I did the boundary and then f sharp, this was the same as f sharp and then the boundary. And from that, we got that this induces a well-defined map on homology. You just hit your representative. So remember, homology is some quotient of the space. So there's always a representative for a homological element, which is a simplex. And if I just hit that with f, I get an element of the homology of y. And here's some easy properties of these maps. If I do f composed with g, and I want to know what that does on homology, it's the same as the map induced by g on homology, and then follow that by the map induced by f in homology. And similarly, if I look at the identity map of a topological space, it's going to induce the identity map on homology. Very easy to see. So our next goal is to step this up. We learned what maps do. Now we want to learn what maps between maps do. And what are maps between maps? They're homotopies. So these are called chain homotopies and homotopies. So now recall that a homotopy between f and g, and these are maps x to y, is a map capital F from x cross I into y with f of x cross 0 being little f and f restricted to x cross 1 being little g. So given a simplex, delta, let's just say it's an n-dimensional simplex, delta n, in x, a homotopy has a natural delta n cross I sitting inside of it. I mean, this is maybe a little obvious, but I'll just draw a picture anyway. Here's a simplex inside of my space x, but a homotopy takes place in the space x cross I, and inside of here, there's the simplex delta. Here, this is delta 2 cross I. And so the upshot is we need to understand delta n cross I. And in what way do we need to understand it? Well, we want to do homology somehow on all of this. So I need to understand how to break that space up into simplices. So, we need to understand this space in terms of simplices. Let's start with some easy examples. Well, delta 0 cross I here's delta 0, it's just like a point. And if I just cross it with I actually already get a 1 simplex. So nothing to do there. And so I'm going to adopt this naming convention where things on the original simplex are going to be called like spans of V, and things on the top are going to be called spans of W. So here on the bottom is V0, and on top I should call this W0. Okay, so nothing to do there. How about a 1 simplex? Well, here's delta 1, V0 to V1, and then I cross it with I, and so I get this filled in square, W0, W1, and here's how I can break this up into simplices. I can draw a line between V0 and W1 and orient things the right way. And so this is going to be span of V0, W0, W1, and V0, V1, W1. Great. Let's do one more concrete example, and then let's see if we can figure out the general case. Here's delta 2 cross I. This one's a little trickier to draw. Draw the top triangle first. Okay, so I'm going to have V0, V1, V2, W0, W1, and W2 up here. And what I'm going to do is I'm going to draw a line from VI to WJ if I is less than J. So V0 goes to W1 and W2 like that. And V1 is going to get a line up to W2 here. And now it's maybe hard to see, but I've broken my space up here into a bunch of simplices. So what are the simplices? I'll give you the vertices, and then you could try to pause the video or something and see if you can see what they are. V0, W0, W1, W2, V0, V1, W1, W2, and V0, V1, V2, W2. So I should see 3 simplices here. And there's sort of like one on the left, one on the right, and one behind. Now, in general, delta n cross I can be broken up into Okay, so if n plus 1 simplices. And these are given by convex hulls of some spaces. It's the union over I of V0 up to Vi and Wi up to Wn. So as a sanity check, I told you this is an n plus 1 simplex. Make sure there's n plus 1 points there. Great, there are. I'm double counting Vi and Wi. Now, if... Oh, sorry, there should be n plus 2 points in there. So n plus 2 points make up the n plus 1 simplex. Now, if sigma from delta n to x is a map, then we get a map. It's the obvious product map. Sigma cross the identity from x cross I, from sigma cross I to x cross I, given by sigma cross the identity of a point in x and a point in the interval t is sigma of x t. So just do the map sigma at every level. Nothing fancy. Now, given a homotopy, f from x cross I into y we define the Prism operator to be the map P from n chains on x to n chains on y given on basis elements as P of sigma is the summation over all I minus 1 to the I f composed with sigma cross the identity restricted to V0 to Vi, Wi to Wn. So just make sure everything here matches. I claim that you should take in some n simplex. So here's your n simplex. And I should output some n plus 1 chain. And this is indeed what I have here. All of these are those n plus 1 simplices, which I broke up sigma cross I into. And then I just mapped them over with the homotopy at a given level. So that was the more concrete world of topological spaces. Now I just want to dip for a second into the more abstract world of chain complexes and give a definition. This is a really tough-looking definition, but we'll see why it is defined as such later. So let Cn with its chain map boundary C, boundary map boundary C, and Dn with its boundary map, boundary D, be chain complexes. And let F and G from Cn to Dn be chain maps. Then a chain homotopy equivalence is a map P from Cn to Dn plus 1, so P increases degree, such that this sort of weird looking condition holds, which is that if I do the boundary of C composed with P plus P composed with the boundary D, I get G minus F. I'm going to draw a diagram here just so we keep track of everything. So Cn plus 1 maps with boundary C down to Cn, maps with boundary C down to Cn minus 1, and I have maps between C and D like so. All right, and this chain map goes diagonally. So Cn minus 1. So slants over like that, P. So just a warning. This is not a commutative diagram. Most of the times when I write down a diagram, it's going to be a commutative diagram. Not this time. All right, so I can go from C to D using F or using G, and in basically all of the instances we care about, we're going to be able to add maps. For example, if these are chain complexes of abelian groups, adding maps makes sense, and so does subtracting maps. So I can map from C to D by this G minus F, this G minus F, this G minus F. Okay. So that's a Dn minus 1, that's a Dn plus 1. Now, there are two ways for me to get from Cn to Dn plus 1. Or let's follow along. So I can do boundary C followed by P, or I can do P followed by boundary D, and if I add those two up, it needs to be exactly equal to this map here, G minus F. And that's a chain homotopy equivalence. A little abstract, but maybe you can... oops, I'm sorry, this is not a chain homotopy equivalence. It is just a chain homotopy. Okay. So, you might be able to guess the next proposition. Here it is. Proposition. If F from X cross I into Y is a homotopy, say between maps F and G, now associated to a homotopy, we define these Prism operators. The Prism operator P, and remember the domain and target, it went from Cn of X to Cn plus 1 of y. So it raises the degree, just like a chain homotopy. And in fact, that's because this is a chain homotopy between the maps F sharp and G sharp. So remember what this means is that if I do the boundary map and then P plus P and then the boundary map, this is equal to G sharp minus F sharp. So I'm not going to go into all of the details of the proof here, but I'll give you the idea. Now, boundary P plus P boundary equals G sharp minus F sharp. I can just rephrase this as boundary of P is equal to G sharp minus F sharp minus P composed with the boundary. Right? And remember, this Prism operator was, you take your n simplex, v0, v1, cross it with I, so w0 to w1, and then we cut it up to little pieces here, and we map over by this homotopy map F. And what is this saying? Boundary of P. So that's everything sort of on the outside of the square. And it's saying it's G sharp. That's essentially the map up here. That's F of x cross 1 once we map it over. F sharp, that's the boundary down here once we map it over. And then I'm going to look at the boundary of the map on the bottom. That's V0 and V1. And then I'm going to do the prism construction of that, which is crossing it with I and mapping it over by the homotopy. And when you do that, you see exactly the boundary of P broken up in this way. So for the actual proof, I'm not going to, again, go into details here, but just can check the formulas directly. There's just lots of cancellations, and it's more trouble than it's worth. Great. So what we've learned is that a homotopy of topological spaces induces a chain homotopy of the singular homology chain complexes. And that chain homotopy is induced by these prism operators. So now let's see what the implications of that are algebraically. So here's a lemma. If F and G from Cn to Dn are chain maps, which are chain homotopic, so remember, chain maps induce maps on homology, then F star and G star, these go from the homology of the chain complex C to the homology of the chain complex D, are the same map. So let's prove this. Well, okay, if F and G are chain homotopic, then there exists a map P from Cn to Dn plus 1 so that, let's just write down the condition again, boundary P plus P boundary is equal to G sharp minus F sharp. Now, if alpha in Cn is a cycle, aka the boundary map is 0, then boundary P of C plus P of the boundary of C is, okay, G sharp of C minus F sharp of C. But, again, remember this cycle condition means that boundary of C is 0, so boundary P of C is equal to G sharp of C minus F sharp of C. Okay, now homology is cycles mod boundaries, right? So if we're ever going to look at the map on homology, it made sense to look at a cycle, right? But now what we have is that G sharp minus F sharp is a boundary. And in homology, we're modding out by boundaries. So G star of C minus F star of C equals 0 in the homology of D. And of course, this means that G star of C is equal to F star of C. So we took anything that could be a homology element, something that is a cycle, and then we show that the difference of the images is a boundary, and so they must be equal in the homology group. Great. So here is our theorem. If F from X to Y is a homotopy equivalence of topological spaces, then F star from Hn of X to Hn of Y is an isomorphism. AKA, homology is a homotopy equivalence invariant. It can't tell apart homotopy equivalent spaces. We pretty much have everything we need now. We've done all the heavy lifting. So let H from Y to X be the inverse of F, so that, as usual, F composed with H is homotopic to the identity, so on X, and H composed with F is isotopic to homotopic to the identity on Y. Okay, then F composed with H star, well, this is, as we said in the beginning of the class, this is F star composed with H star, but also F composed with H star is equal to the identity map. Why is that? Well, we've also shown that the identity map on a space induces the identity map on homology. And in the previous proposition, the one immediately preceding this, we said that homotopic maps induce the same map on homology because they induce chain homotopic maps, right? So F star composed with H star is equal to the identity. And similarly, H star composed with F star is equal to the identity map. And just so we remember where we're at, this is the identity map on the homology of Y. And this is the identity map on the homology of X. And so F star and G star are inverse group isomorphisms. And there we have it. So just like the fundamental group, singular homology is a homotopy equivalence invariant of a space. So that's going to do it for this class. Just as a little summary, you can view this result as a sort of good or a bad thing. On one hand, you can't tell apart spaces that are homotopy equivalent but not homeomorphic. On the other hand, if I'm just interested in computing the homology of some group, I can modify it by any homotopy equivalence I want and just calculate that group. So for example, any contractible space has the homology of a point, which is to say 0 in the 0th level, H0 is equal to Z, and all of the other groups are equal to 0. So thanks, and I will see you again next time.